Thanks for tuning in to Statistics Made Easy. In this session, we focus on interpreting the results of a nonlinear regression model, which is different from the case of a linear regression model that we looked at in our previous video. Here we have an example of a probit regression, which is used to predict a binary dependent variable. Let's begin by looking at the syntax of this command. We first have our regression command, followed by our binary dependent variable, where 0 means that our customer is an adult and 1 means that our customer is a child. Then we have our predictors, temperature, and the location of the ice cream parlor as here specified. In the probit regression, we have a maximum likelihood estimation, which is an iterative procedure. The first iteration, which you see at the beginning of the output, is the log likelihood of the model, or the empty model, that is a model with no predictors. At the next iteration, called iteration 1, our explanatory variables are added to the model. At each iteration, the log likelihood increases because the goal is to maximize the log likelihood. When the difference between successive iterations is very small, the model is said to have converged and the iterating stops. If you compare iteration 1 and 2, you see that the log likelihood is identical, so the iteration stops, and the final value of the log likelihood is then displayed here as log likelihood. The log likelihood here per se does not have any useful interpretive meaning. However, if we have different models, for example, one model in which you only include the control variables and another model in which you also include the explanatory variables, you will typically see that there's an increase in the value of the log likelihood. That means that the additional variables that you add into your second model carry some explanatory power over your dependent variable. Now, let's look at the details of the output. Again, we first see the number of observations. Remember that it is important that you have the same number of observations across all the models. And you can check out the corresponding video on how to make that happen in Stata. Next, you have the LR chi-squared value. This is the likelihood ratio chi-squared test that at least one of the predictors in your model is not equal to 0. In other words, whether one of these explanatory variables that you have in the model has a coefficient that is either larger or smaller than 0. Next, we have the test of significance for this likelihood ratio. Given that in this case we have a very high p-value, we cannot reject the null hypothesis that all of the regression coefficients in our model are equal to 0. What is a high value? Well, typically you take thresholds that are randomly defined of 5 or maybe 10%. But in any case, our value clearly exceeds any threshold. Going into detail, we now also have our results for the covariates. For example, we have temperature and we see our coefficients, the standard errors, the z-value and the p-value. In the case of nonlinear regression models, we have to be a little bit careful in interpreting the coefficient. We can always interpret the sign of the coefficient. In this case, it's a negative sign. However, we cannot interpret the coefficient size. This is only possible in a linear regression model where we have a straight line for our regression estimate. But here with the maximum likelihood estimation, we cannot interpret the coefficient sizes. So the only thing that we're left with at this point is to say that temperature is negatively related to being a child. But wait a minute, we also have to look at the statistical significance, of course. Here we have our standard error and our z-value and p-value, which indicate whether this relationship that the coefficient shows is statistically significant. Here we have a very high p-value again. Given our sample, we would probably accept p-values around 5% or even going up to 10%, but this value clearly exceeds any possibly set threshold, which means that we cannot reject the null hypothesis that the coefficient is equal to 0. In other words, we cannot make any claim about the relationship between the temperature and the likelihood that the customer is a child, which confirms our early impression from the likelihood ratio that all of our coefficients are equal to 0. Then we also have our control variables, in this case whether the ice cream parlor is in the park or next to the train station. Again, we see that the p-values are very high, so we cannot reject the null hypothesis that these coefficients are equal to 0. Again, this very much reflects our earlier estimate that all the coefficients are apparently not different from 0. In sum, what we can see in this model is that all these explanations, temperature and location, cannot predict whether our customer is a child or not. If you're interested in estimating the effect sizes in nonlinear models, you can use the margins command in Stata, which allows you to calculate the marginal effect of an independent variable at different values of the independent variable, for example, at a 1 standard deviation below or above the mean value or at different percentile values. Check out my video on moderation analyses for practical examples. Thanks for watching.